Okay, hello everyone. This is Jim Rogers, and I am going to be covering Chapter 2, the first lesson in Chapter 2 on basic plotting for MI205, R for Pharmacometrics. When I did this class live a couple days ago, we recorded it, but there was a problem with the audio, so this is not an exact capture of what I taught in the actual class, but I'll try to go over all the key content. I'm going to do it probably a little bit quicker than I would have in the class because we won't have the back and forth of questions. But again, it should provide a record of what we talked about. This is starting in on plotting. And plotting is one of the areas where we feel we can kind of give you a lot of bang for your buck quickly in terms of R programming. It's one of the reasons a lot of people come to R in the first place. Is it just makes really nice graphics. And it's also a nice way to learn about other aspects of the language. The decision that we've made, there's a lot of graphics functionality within R, much more than we could ever hope to cover in this course, even though we're devoting 3 lectures to it. The decision that we've made is to focus on a package called the Lattice package. So this was written by Deepan Sarkar when he was a graduate student, and he still maintains it. I'm actually not sure where he is now, but Lattice was based on the trellis system, which goes back to a book called I think it's called Visualizing Data by the last name is Cleveland. And it incorporates a number of concepts, but the most recognizable feature of these trellis type graphs is the fact that they're often multi-panel displays. But that doesn't mean that it's only useful for multi-panel displays. You'll see a number of examples that we will do that are not multi-panel. And so really Lattice is just a nice general purpose plotting set of plotting functionality. And so that's why we focus on that. And I wanted to kind of situate you with respect to where Lattice lies in the bigger picture of R graphics. And so there's a diagram here on page 22 of your book that is meant to sort of show how there's kind of low-level plotting functionality in R, and on top of that is built some higher-level functionality, and on top of that is some very specific higher-level functionality that might be specific to certain data types. And the package we're going to focus on again is Lattice, which is kind of here in the middle. It's not highly specific to any particular data type, but it's also not so low level that you end up saying, put one point here that's this, and specifying how big it is and all that. It takes care of a lot of the details that you usually don't want to worry about. Lattice is built on another lower level package called Grid. Grid is an amazing system. It's extremely versatile, about as versatile as you could imagine a statistical visualization system being. But it's so versatile that it doesn't provide you enough of the nice defaults that make life easy and convenient. So we're using this higher level thing, Lattice. a couple things, though, a couple important implications of Lattice being built on top of grid is number one, even within R, there's a whole other set of graphics functionality called traditional graphics. So this was the first sort of graphics paradigm within R. It involves functions like plot and hist and some more specific plotting functionality. And the caveat here is that plotting code that you write using traditional graphics doesn't generally transfer to what you might do with Lattice and vice versa. So that's what this solid black line here is in the middle. It's kind of a, indicating that there's not much transfer from one side here to the other. Additionally, an implication of that for any of you that might use S+, the S+ graphics are just in the traditional graphics paradigm. And so what we do in Lattice is actually generally not going to transfer very well to S+. There's an analogous package in S+ called Trellis, but Trellis is, superficially it's similar to Lattice, but if you look under the hood, Trellis is built using traditional graphics functionality. And so as soon as you get into a moderately complex example, the code that you might have developed in S+ using Trellis is not going to work in Lattice and vice versa. Personally, here at Metrum, we don't really care because we only use R. But for those of you who may go back and forth, that's just something you need to be aware of. Okay. The one other thing I wanted to mention, and I should update this in this graphic here, is there is another sort of what I'm calling high level, or you might call it mid-level package in R that's very cool in terms of what it can do. It's called ggplot2. That's also one that we have considered making part of this course, and I may be able to cover that a little bit on the last day. Is kind of similar to Lattice in terms of the level of the granularity of control that you have. Although in some ways ggplot2 is more powerful. We thought it over, and again, we think you get more bang for your buck by focusing on Lattice. So that's what we're going to do. So hopefully that helps kind of situate where Lattice is in the bigger picture. And so what we're going to do now is I'm going to move over to our RStudio server. And I've loaded the R script basicplotting.r, which you can get off the course website. I first made a folder called Basic Plotting, and I put my basic plotting script in there, and so we will work off of that. I've opened that script up here. So what I'm going to do is I'm just going to start with, let me make this a little bit bigger. Hopefully that is good enough to see. We're going to go through chunk by chunk here. The first chunk you don't really need to understand for now. You can try to understand it. It's not that complicated. But that's not really the focus of the lesson today. Just go ahead and execute this first chunk. It's just going to create a data set for you called DAT. And if we go down to chunk 3 here, here's a trick you can use with a lot of different data sets. Well, first of all, before I show you that, one way to get a quick look at what's in this data frame called DAT is to use what's called the head function. And so that means just give me the first few rows of DAT. So I guess by default it gives you 6 rows. And that's usually fine. That's what actually I do and a lot of us do, is just take a look at the top of a data set. Although if you want to be safer in a sense and make sure you get a more robust view of what's in the data, one thing you can do is take a random sample of, these are the numbers going from 1 up to the number of rows in DAT, and I can just pick 10 of those. So it's basically amounts to picking 10 rows, and then I can take those randomly sampled rows and display those rows from the data frame DAT. So that's what I'm going to do. Oops. I'm going to make sure to submit both of these lines here. Okay. So basically, it's a relatively simple data set. You've got a subject identifier, a time variable, which is month, dose, exposure, meaning the concentration of the drug, let's say in circulation, and then some response variable. So that's kind of along the lines of the structure, simplified structure that you often come across in problems in pharmacometrics. So that's what we're going to work with. And we'll kind of jump ahead to a little bit of fun stuff and then do a little bit of stuff that's not as interesting, but it's necessary. So right off the bat, let's just make a plot. And this is a plot with the traditional plotting function, traditional graphics plotting function called plot. Since you guys are new to R, let's break down the pieces here first. So DAT dollar exposure, I'm going to just copy that and paste that down in the R prompt. That's just a vector of numbers. That's the exposure column from the DAT data frame, right? And then same for DAT response. So that's just a vector, okay? Same with DAT response. This is just a vector, and it's the vector of values that were in the response column of DAT. All right? And so plot, we can just pass it an X vector and a Y vector, and it will make a scatter plot. You know, of basically what you would expect. So, so that's the simplest possible example. Now, right off the bat, you're going to see a lot of things that you probably want to change, like, you know, how do I change these X labels and Y labels, and how do I put a title on? We will get to all that. I just want to show you what you can get quickly by default for now. So now that we've had a little taste of actually generating a plot, let's go back and do that stuff that I said is not necessarily so fun. Let's see. I'm going to depart from the script for a second here and show you that every time we issue a plotting command, whether it's traditional graphics or Lattice, or you know, grid-based graphics, every time we issue any sort of drawing command, R is going to send that drawing command to a graphics device. So a device is just a generic term that means kind of like somewhere to record, somewhere to do the drawing. Okay? So right now you can see we're using RStudio, and there's an on-screen display area here, and so all the drawing instructions are going to get sent to that on-screen area. And that's actually a device, and that has a name. And if we want to find out the name of that device, we can do dev.cur, open paren, close paren. That stands for current device. And basically it's telling us that this screen device that's being used now is something called RStudio GD. which I'm sure stands for RStudio graphics device. If you were using sort of the regular RGUI install and not RStudio, you'd have a different device that would have popped open, and it depends on what type of computer you're working off of. I can't remember anymore what you get on Windows. On a Mac, you would get, I think, a device called Quartz, or you might get one called X11. Also, if you're on Unix or Linux, I think you'd probably get an X11 device. You don't really need to worry about the details. The point are, there's a number of graphics devices that are just screen-based devices. They're going to put a plot on your screen. There's also a lot of devices that are file-based. So rather than sending those drawing instructions to a screen, it's going to send all the drawing instructions to a file. So an example of that, we're going to jump back to chunk number 4 here. And this function PDF opens up what's called a PDF device, which means it's going to write a PDF file. And so we're going to execute that. We're going to pass it an argument and say, the file that you're going to write, we want it to be called test.pdf. So I'm going to run that. And now I'm going to run, actually first let me clean up my files here. Just so you don't think I have anything up my sleeve here. Clear out my files. I'm also going to set my working directory, which I do with set WD. I'm going to set that to be basic plotting. So in other words, it's going to use this folder that I have here, basic plotting, as my working directory. Whereas by default it would use the parent directory. And you'll see the implications of using that as a working directory in a second. Now if well, actually let me be careful here. I need to first, what I'm going to do, because I've confused things by kind of jumping in midstream here. I'm going to kind of go back to square one, kind of like the way it was when we first started up. I'm going to turn off all the graphics devices. Now we don't even have our on-screen device. And now I'm going to go back, now that my working directory is basic plotting. I'm going to, again, execute this PDF, opening up this PDF device. Now I'm going to send a plotting command to it. Okay. And now you might say, okay, well, let's go and look. Is that file there? And if you open up your basic plotting folder, if you made that your working directory, you should have what looks like a PDF file there, test.pdf. But if you try to open that up, you'll get nothing. Even though we've already sent some drawing instructions to it, but we haven't, PDF file has kind of a header and then a bunch of content and then a footer or a closing, some closing arguments. And basically we haven't finished writing that file. So we can, I'll go ahead and do this other thing here. We can, while that device is still open, we can send additional drawing commands to it, like this AB line h equals 50. That's going to add a horizontal reference line, and it's going to be the line y equals 50. Okay, so I'll do that. And I could keep going. I could keep adding more and more things to the plot. Whenever I'm done, I'm going to do dev.off. And now, if you were watching closely, or if your eye just kind of captured it, the size of this test.pdf file just changed. It just went up to 12.4. And now if you click on that, Now it's a valid PDF file. And you can put that in your report or whatever you want to do. Now, maybe, hopefully, just to say the obvious here, I could have done the same thing without ever opening up a PDF device. And what it would have done there is it would have used its kind of default screen device, which is, again, the RStudio device. I'm going to run that code. And now it's putting it back here because I've closed up that PDF device. It's not going to send the drawing instructions there anymore. It's going to send them to the default screen device, which in this case is RStudio GD. So that's how devices work. It's kind of hitting you on the head right off the bat with something that's potentially confusing. If it's a little bit confusing, I think that's okay. I think eventually you get the hang of that. Now we can move on to the fun stuff, okay? I actually don't remember what I was trying to illustrate with this chunk number 8, other than perhaps, you don't need to be plotting stuff that's in a data frame. Any vector will do. So I might just have the vector of numbers from 1 to 10, which, let me just copy that and paste that down here so you can see what 1:10 looks like. That just constructs a vector of integers going from 1 to 10. And then I could plot that versus the numbers going from 11 to 20. And there it is, okay? Now we're going to start to get into a more complex example, and it's going to kind of seem a little bit cumbersome, and that's on purpose, and then I'm going to show you how we can make it not so cumbersome. So what I've done here in this chunk number 9, let me try to break this down. You already know that well, first of all, let's look at a high level here. I'm still using the traditional graphics plot function, and I'm still passing it 2 arguments. This is going to be the x vector, and this is going to be the y vector. Well, sorry, not that last parenthesis. That's going to be the y vector. And to make it a little bit more complicated now, I'm saying don't just give me the values of don't just give me all the values of exposure. Give me the ones, and I'm doing some subscripting here, give me the values where dose is not equal to 0. Now I don't think you've seen how this works, but let's break it down piece by piece. And this is a general trick. You should just kind of, anytime you're trying to figure out somebody else's code, and it just, doesn't really make sense to you, just kind of work from the inside out and try to understand all the little bits one by one. So if I take this dat $dose, that's the dose column, and the exclamation point equals means not equal 0. Let's see what that looks like. Just that by itself. That is going to give us a vector of trues and falses. So it's going to be true wherever dose is not 0, and it's going to be false wherever dose is 0. And so now when I use a logical vector like that for subscripting, let me show you a real simple example. I could say, I could have a vector called x, which is just the first 5 letters of the alphabet. So capital, all caps letters is a special reserved word in R, meaning just what you think, the capital letters. And like any vector, x could be any vector, I can subscript it with just telling it true if it's an element that I want, false if it's an element that I don't want. So if I do this, the only elements I'm going to get back are the first and the fourth, which is A and D. And so that's what I get back. So we're doing the same thing up here. This is saying give me all the values of exposure where dose is not equal to 0. Okay. And that's going to be, well, and then take the log of that. And that's going to be my x vector. And then I'm going to do something similar for my y vector, but there I'm going to take response where dose is not 0. Okay? So nothing really new here in terms of the plotting functionality that I'm trying to show you. This is more like I'm trying to show you some of the typical things you might want to do on the fly, which is taking a subset of the data, transforming the data with a log transform maybe, or some other kind of transform. I forget what I was trying to illustrate here. For now, for whatever reason, I'm taking the log of x instead of the log of, oh, I'm sorry. This chunk number 10, ignore that last sentence. This chunk number 10 is what I'm trying to show here is what's called the formula interface. So this is going to actually, if you execute chunk number 10, you're going to get a plot that looks exactly the same as when we executed chunk number 9. And if you look for where the difference is, there's two differences. One is that before we had a comma, and now we have a tilde. And before we had the x variable first, and now we have the x variable second. Okay? And so this is what's called the formula method for the plot function. And right now it might seem kind of pointless. It's like, why do it one way or the other? You'll see that in a second. The thing to understand really is that anytime you see a tilde in R, that's what's called a formula constructor. And a formula is just a thing that specifies a relationship between two variables. And we'll leave it at that for now, but you'll see, we'll come back later and see how formula is used in other ways. What it does, though, is it means this whole thing, we're no longer passing the plot function two vectors. We're now passing the plot function one formula. Okay? You don't have to understand what all these terms mean. The point is, it's just a different interface to the plot function. Now, where that becomes useful is shown in chunk number 11 here. When you use the formula interface, you can take some of these elements that get repeated, like up here in chunk number 10, we referred to the data frame dat 1, 2, 3, 4 times. That seems like kind of cumbersome to have to keep writing that out. So down here in chunk number 11, we can just pass in a separate argument that says data equals dat. And then it knows that any variable we give it, like response, it should go looking for that variable within the dat data frame. It's the same with the subsetting. So whereas up here we did that subscripting on the on the y variable, and we took the same subset on the x variable, well, we can just pass. Remember that logical vector of trues and falses? We can pass that as the argument to subset. And so that's it's a little bit more elegant, and it's just a little bit less typing, basically, which comes in handy when you're doing a lot of this. So that's how the formula interface works. And that's available in traditional graphics, and it's also available, it's really the primary mode of interacting with lattice graphics. All right, I'm going to move to, in chunk number 12 here, all I'm trying to show is that some of those questions you might have had when you saw those first plots, you said, I don't like that X label or that Y label. Well, there's arguments for a lot of that stuff. Like here, this is main is the title of the plot, X lab is the X label, Y lab is the Y label. So you can see if we execute this, now it's says something, you know, on the y-axis it says Dr. I Know Best assessment scale and so forth. So it's just a way of prettying up your plot. If you want to know what the other arguments are, you can look for documentation on the plot function. But I wouldn't suggest that. What I would suggest is we're going to be, again, focusing on what Lattice can do. We're going to move over to Lattice plotting functions in a second, and I'll walk you through that documentation for the Lattice XY plot when we get to it. What was I trying to show here? I guess what I'm trying to show in chunk number 13 is in the traditional graphics paradigm, the way that usually works is you make a plot, and so let's start with, this is the same plot we already have, okay? And then you add to it. So, or not, I mean, you might just leave it as is, but you kind of typically will just build on top of that. And so the first time you use the function plot, and that doesn't just plot points. You can see that makes axis labels and tick marks, and it inlays the plot with margins around it. So there's a lot of extra stuff that plot is doing. But once that's there, a lot of times you just want to add to the actual plotting region itself, not to the margins or anything like that. And so that's what points does. Points is just adding points. So in this case, I'm going to add a point for right where the mean is, okay? The mean of the x values and the mean of the y values. And there's, so you look over here, there's that big solid point. The solidness I got by specifying PCH equals 19. The bigness I got by specifying CEX equals 2. And now I can add some reference lines. You don't need to worry about the details of this too much. The point is, I'm gradually just it's kind of like I'm pasting stuff on top of this plot. And when we get to XY plot, it's going to be kind of different. You know, instead of building it up incrementally, we're going to kind of just make it all at once when we move to the lattice function XY plot. Okay? So that's your real quick look at traditional graphics. From now on, we're going to start with, we're going to do everything else with lattice graphics. And I think this is a good break point, actually. This is about where I left off in the actual live lecture. So, so that's what we're going to do here as well. That's hopefully where the fun will begin. Okay, so that's all I've got to say for today, and tune in for the next lecture, and we'll really get humming on doing some useful things. All right, thanks everyone, and I'm signing off.